Okay, everyone, welcome back. Our second speaker is Professor Shi from Yale Mathematics Science Center of Tsinghua University. He is also a part-time professor of our DIMSA. His research interests include numerical methods for partial differential equations and image processing. He also conducted a lot of research on math for AI. The title of his talk is PDE-based models in semi-supervised learning. Let's welcome Professor Shi.
Thanks, Fan for the introduction. It's a great honor for me to talk about our recent work in PD-based model in supervised learning. As mentioned by Fan, I'm also joined appointment in the institute here. So I also joined the organization of ICBS. So in some sense, I'm also host of this congress. If I want to welcome all of you to participate in this congress, and any of you, if any one of you have any question about the congress, feel free to tell me. Okay. Today I will talk about the PDE-based models in semi-supervised learning. Semi-supervised learning is a topic studied in a machine learning program. From mathematical perspective, it can be formulated as an interpolation or extrapolation problem. Suppose we have a bunch of data, and this data can be viewed as a bunch of vector points in high-dimensional space. For example, if we have a bunch of images, and each image is a 100 by 100 resolution, and for each image we can see it as a point in 10,000 dimensional space, and we have millions of these images, this kind of images. Then we have a lot of points in this very high-dimensional space. And suppose we want to classify these images, and we have labels in some image. For example, we labeled this image as a dogs, the other image as a cat, and for partial of the image, we have labels, and most of the image, we don't have labels, and we want to inference this unlabeled image. And this, from a mathematical perspective, we can formulate it as an interpolation problem. So, but we have a bunch of points, and at some points, we have labels, and we want to get the labels on other unlabeled points, right? So we want to get a function of u from the point cloud to real value, for example, and this is some kind of interpolation problem. And for the classical interpolation problem, for example, in one-dimensional or two-dimensional, it is a very classical problem studied in numerical analysis. Actually, in the course of numerical analysis, we also we also teach this kind of problem. For example, polynomial Lagrange interpolation or some cube spline or some kind of interpolation. But here we are dealing with a bunch of point cloud in very high dimensional space, and this point do not have any structure. This unstructured data, and we want to get a function u defined on this point cloud. And if we want to get a reasonable function, we have to impose some condition or assumptions on this function of u. Otherwise, the value of u can, the function of u can be any value in the unlabeled points. One popular assumption on function of u is that we assume u is a smooth function. U is a smooth function, and sorry, I forgot to mention that usually we assume but now we only have a bunch of discrete points. In what sense the function defined in a discrete point cloud is a smooth function? So when we said U is a smooth function, we actually has another assumption on data. We assume data lies in a smooth manifold. And this function is a smooth function defined in this smooth manifold. So basically, here we have two assumptions. One assumption is on the data, and the other assumption is on the function u. We assume the data lies in a smooth manifold, and the function u is a smooth function in that smooth manifold. And we want to find a smooth function interpolate the data. Now we have to choose a measurement of the smoothness. One simplest and popular measurement of the smoothness is that the outer norm of the gradient. It's a simplest one in to measure the smoothness. If we use this measurement, then we want to actually we need to solve this kind of problem. We want to minimize the outer norm of the gradient view. Here, the gradient is defined in the underlying smooth manifold. And with this constraint is that we want to interpolate the labeled data, right? So G is a labeled value in the labeled points. And this problem is a very classical problem studied in numerical analysis of variational calculus. It is well known that the solution of this problem can be given by solving this Laplacian spectrum equation with this constraint. This constraint is a kind of boundary conditions, usual boundary conditions, which are defined in the manifold. And this is the classical Laplacian spectrum equation defined on the manifold. This kind of problem has been the Laplacian equation, the numerical method for the Laplacian equation has been extensively studied in traditional numerical analysis, but it is confined in the Euclidean space. However, here we need to solve it in a very high-dimensional structured point cloud. We need to have some develop some new mathematical, new numerical method to solve it. One popular method is a so-called graph Laplacian. It is very simple. Actually, it can be, let's look at this Cauchy problem of the diffusion equation in Euclidean space. It is well known that this equation can be solved using the Gaussian kernel. But if we look at here, we just want to discretize the Laplacian operator. So we look at this equation oppositely. On the other hand, if we have the exact solution of this equation, and then we can approximate the Laplacian operator in this sense. We just take the first order difference, forward order difference at the time at t equal to 0. Then we get this approximation. And here Vx0 is just the initial condition, and the Vxt can be given by integral of this Gaussian kernel. And then we have this integral approximation of the Laplacian operator. Then later, in the machine learning community, it just generalize this approximation from the Euclidean space to the manifold. Then it gives us this integral approximation in the smooth manifold. Then we can approximate the original Laplacian spectrum equation by this integral equation. And the advantage of this integral equation is that it can be easily discretized over unstructured point cloud, just replacing the integral by summation. So then we can get this linear system. Then we solve this linear system, and we can get the value of u on the unlabeled points. It can be proved as if number of points goes to infinity such that it samples a smooth manifold, then this graph Laplacian converge to the real Laplacian batch may operate in this rate. However, let's see a very simple example to see the performance of this graph Laplacian. Here we just using this toy example is in one-dimensional space. It's just a one toy example. We sample the interval 0 to 2 using 5,000 points. And we label the 6 points. This red circle is labeled points. And we using the graph Laplacian to solve to try to interpolate this 6 red circle. If we want to solve the Laplacian equation in one-dimensional space, we know that the ground truth is that the strict segment connect all these 6 red circles. However, the solution given by the graph Laplacian is like this. It has jumps at the labeled points. It's not even continuous. The original motivation is to find a smooth solution. However, the solution given by graph Laplacian is not even continuous. So this means that the solution of graph Laplacian cannot interpolate the labeled points. Maybe some people say that this example is too simple. It's just one dimension. Now let's see another more complex example. It is extracted using the image imprinting problem. Suppose we have a original image. This and we cut this image to small patches. Here we use a patch. The size of patch is 11 by 11. So we cut this image to the small patches, and each patch, since the size is 11 by 11, it can be viewed as a point in 121 dimensional space. Then we have a bunch of points in this high dimensional space, and then we can. This is a point cloud in this example. Then we construct a function defined on this point cloud. For the function of u, we define its value on each patch is the intensity of the central pixel of this patch. Then we define, we construct a function in this point cloud. This is the ground truth in this example. Okay, then we pretend we only know 1% of we only have 1% of labeled points, which means that we only know the function of u on 1% of the patches. On 1% of patches. And we solve that graph Laplacian to get the function of u on other patches, on the unlabeled patches. This is a result given by graph Laplacian. Because we constructed the function of u of the central pixel of the patch. So actually, the function of u is just this image. It's just this image. And we can see that it has some maybe you can see that it has some pixels it seems that it's not consistent with the background. All right, let's zoom in. If we zoom in some area of this image, we can see that this is a result given by the graph Laplacian, and this is a labeled data. This is a ground truth. This is original image. As we can see that at some pixels, this pixels is not consistent with the background. However, if we look at if we compare the labeled image and the reconstructed image, we can see that all these inconsistent pixels are actually the labeled image. So this phenomenon is actually the same, exactly same as the previous toy example, which means that the solution given by graph Laplacian is not even continuous. It has jumps on the labeled points. Okay. Why the graph Laplacian has this discontinuous phenomena? Actually, we can look at this problem from another point of view. So first, the original problem is that we want to solve this problem, optimization problem. Now, let's discretize this gradient using this so-called non-local gradient. And then we can get this discrete optimization problem with this constraint. It says also well easily actually this optimization problem is equivalent with the graph Laplacian. The solution of this problem can be given by the linear system in the graph Laplacian, actually. Now let's look at this problem in another way. We can separate this summation to two parts. The first part is the summation over the unlabeled points, and the other term is the summation over the labeled points. And why is the solution given by the solution of this optimization problem is discontinuous on the unlabeled points? If the solution is discontinuous, this term should be large, right? It has a jump at the label points. But if we want to minimize this objective function, how comes this term become large? The reason is very simple, because the summation, this term, the summation is the number of terms in this summation is small, comparing with the previous one. Suppose let's recall the examples we consider. In the first example, in the one-dimensional example, the number of points is 5,000. The labeled points is only 6. And in the second example is the label rate. The labeled point is 1%. So which means that the number of terms in this summation is much less than this one. So these two terms is not balanced. Okay. So if we want to remove this continuous phenomena, it's very simple. If you have based on this observation, it is very simple. We just add one weight in front of this labeled term to balance these two terms. And the value of this weight is very easy to choose. It is just choose to be the ratio between the labeled points and the unlabeled points. It's very, very simple. Okay, after adding this weight, we also get a linear system, very similar with the linear system in the graph Laplacian. The only difference is that here we have this weight. This weight is a large weight, a positive large number. Actually, with this large weight, this linear system is easier to solve than the previous one because we actually add a large number in the diagonal of the coefficient matrix. It even converges, if we use the conjugated gradient to solve it, it converges faster than the previous one. Okay, let's see the performance of this new method. This is the result given for that for one-dimensional example. Actually, it at least give a continuous interpolation. For the second example, this is the result given by this new method, weighted Laplacian method. It is at least continuous. This continuous phenomena are removed. Okay. Let's try another very classical semi-supervised linear data set. It's a MNIST data set. And in this data set, we have 70,000 images, and each image is 28 by 28. So totally, we have 70,000 points in 28 square dimensional space. And in some of the image, we have labels, which means that we, in some image, we label this image as 4 and this image as 2, for example. And we want to get the label of the other images. If we here we just label the 100 randomly labeled 100 images in this data set, and we try. We do 5 independent tries, and to select the labeled points at random. And we can say that if we use the graph Laplacian, this is the correctness of the results given by graph Laplacian, and this is the result given by our new method. It is much larger than the graph Laplacian. And also, if we reduce the label rate from 100 to 50, it the improvement is even larger. So let's say another example given in the image in painting. In our previous example, we also do this kind of problem. However, in that example, it is not a real image in painting problem, because in that example, we use the original image to construct the patches. The patches is from this original image. So it is not a real image in painting method. However, it can be modified very easily to do image in painting. The method is as following. First, for example, we will have a subsample image only have 10% of the pixels is known in the original image. And first, we just fill in the missing pixels random. Then you have a whole image. The image is the original. This image is very, very bad, but at least it is a whole. We know the pixel of each we know the intensity at each pixels. Then we can extract the patches from this image. we construct the point cloud by cutting the image to patches, and then we do that numerical method iteratively. We solve that interpolation to get a new image, and from that new image we can extract the patches, and we do this iteratively, and then we can get a real image painting method. This is a result given by our method, and this is the result given by graph Laplacian. As we can see that in the graph Laplacian, it has that discontinuous phenomenon. But at least our method is much better than the graph Laplacian. Okay. The method is very, very simple, very simple. But why it works? Why this simple method works? It can remove the discontinuous. We can explain it using so-called non-local model of the Laplacian Bertrand equation. So first, originally we want to solve this Laplacian Bertrand equation with some discrete tertiary boundary conditions, and in the non-local, we find that this Laplacian Bertrand equation has this kind of integral approximation. The first line is exactly the same as that given in graph Laplacian, that is using in graph Laplacian. The difference is on the second line. The second line is given by the boundary. The boundary corresponding to the labeled points. In graph Laplacian, this boundary term is dropped. However, this boundary term is not small for derivative boundary condition. Because here, this is a normal derivative, this is a Newman type boundary conditions. However, in derivative problem, we do not know this value. But this value is not small. So we have to include this boundary term to get a correct numerical method to deal with the derivative type of boundary conditions. We can prove that, we can show that after including this boundary term, it has some convergence in R2 norm, and in manifold the analysis is in some sense very tedious. It has some because of the complicated geometry structure, but the idea is very simple. We just using the integration by part and the Taylor expansion. Very, very simple. First, let's show the analysis in the Euclidean space to show the main idea of the analysis. First, we do integration by part. With a given kernel function, we can do integration by part to get this equation. And this is the boundary term we get. And the purpose of this analysis to remove the differential operators, because we do not know how to discretize the differential operators over the point cloud. We want to remove all differential operators. Here we only have this. Here, this is the only differential operators we have. If we want to remove these differential operators, the most natural way is to using the Taylor expansion. Here, this one is just the first order term of the this difference using the Taylor expansion, right? If we replace this one by this difference, then all differential operators disappear. However, unfortunately, we cannot do this simple approximation. The reason is that this approximation is second order. The accuracy is second order because we have this is the first order term in this Taylor expansion. So the error is second order. However, in this in front of this integral, we have this factor 1/delta square. So the error of this approximation is also order of delta square. So if we do this approximation, the total error is order 1. So we cannot do this simple approximation directly. Then how to do the approximation? The idea is very simple. We just include a high order term in Taylor expansion. However, if we include a high order term in Taylor expansion, we just have a second order derivative. We want to remove the first order derivatives, but we include the second order derivatives. But unfortunately, this second order derivative can be reformulated. It is actually equal to we can get the Laplacian original Laplacian operator and some error term. This calculation is also based on the integration by parts. Very direct, very straightforward calculation. And finally, we can get this approximation. This kind of the first line is just the formula are shown in the previous slide, and this the second line is just some error terms. We can show these terms are small in R2 now. Okay, as I mentioned earlier, if we use this integral approximation, we actually have this bounded term in the integral equations. However, in graph Laplacian, this integral term, this bounded term is dropped. This is the reason why the graph Laplacian has that discontinuous phenomenon. If we include this bounded term, we can prove that the solution of this integral equation actually converge to the original Laplacian Bertrand equation as delta goes as t goes to 0. Okay. This is the first method. This is the first method. However, if we reduce the label rate further, for example, if in that example, if we only label 1/1000 patches, and even in the results given by our weighted method, it still has some inconsistent pixels. This kind of discontinuous phenomena emerge with so small label rate. Okay, how to deal with? Actually, this phenomena can be explained using the embedding of Solev space. Since the original problem we want to solve is this kind of optimization problem, here we only minimize, we only have control of the H1 norm of U. However, we can easily prove that if the dimension of the manifold is larger than 3, the optimal solution of this problem is just a constant. It's just a constant, which means that actually the optimal solution of this problem is not the solution we want to get. It can be explained using the Solev embedding. We know that WSP, the space WSP, is embedded to the continuous functional space if this condition is satisfied. Here D is the dimension, and P is the FT norm we're using. And S is the order of derivatives we take. If we want to make the interpolation is continuous at least, we have two ways. Well, we have to make this condition is satisfied. Because this condition is satisfied. Here D is a fixed number. We cannot choose. However, we can choose S or P. So this just gives us two ways to make the interpolation is at least continuous. First one, we increase P. The second one is increase S. Okay. Then if we choose to increase P, then we can increase P to infinity. Right? So we take the extreme case. We increase P to infinity. Then we need to solve this optimization problem. We minimize the infinity norm of the gradient with this constraint. The solution of this problem is at least Lipschitz continuous because we have control of the infinity norm of gradient. Okay. However, the solution of this problem is not unique. It's not unique. So we add regularity term using the R2 norm here to make the solution is unique. So here now we need to solve this problem. This problem is more difficult to solve than the previous R2 minimization problem. However, it can be solved efficiently using the so-called ADMM method. Okay, we can. This is actually this is very standard in the ADMM method. It can be solved iteratively, and this is the one approach to get a continuous interpolation with very low label rate. The other approach is to increase S, right? We increase S. However, here D, we fix P as a 2, still a 2. And here we want to increase S to make this condition is satisfied. However, D is usually very large. We cannot, in practice, we cannot deal with so high order of derivatives. Suppose maybe D is 100, for example. If P is 2, then we theoretically we need to choose S is larger than 50. In practice, we cannot deal with so high order of derivatives, but at least it gives us some guidance. The high order derivatives helps to get a continuous interpolation. So we only increase S to 2. The original one, we take S as equal to 1. Here, we just increase S to 2 to have this term. We also minimize the R2 norm of the Laplacian of U. And we have this model. And yeah, this model also has some improvement over the original first order model. Okay, because we increase the derivatives from 1 to 2. okay, in the image implanting problem, also the second order model gives some improvement over the first order model. Okay. The last part of my talk, I want to give an introduction of the PDE model, general PDE models. In the previous part, we actually show 3 PDE models. One is based on the Laplacian-Beltrami equation, and the other one is infinity Laplacian. Actually, we want to minimize the infinity norm of the gradient, which gives the infinity Laplacian. And the third one is minimize the L2 norm of the second order derivative. Actually, it gives us a biharmonic equations because we minimize the L2 norm of the Laplacian operator. So we have 3 different kind of PDE models for semi-supervised learning. We know that the PDEs, we have an infinite number of PDEs. If we try the PDEs one by one, we cannot finish. So the other natural equation is that a natural question is that can we derive some general form of the PDEs we should use in machine learning? Or this is our original work. We just build a general PDE models for residual type neural network. We view the neural network as an operator, which map a simple function to a complex function. The simple function in the neural networks act as actually corresponding to the output layer. The output layer of the neural network is usually very simple linear functions. But the whole neural network, if we see it as a function, it is a very complex nonlinear function. In some sense, the neural network, we can view it as an operator, which maps the simple linear function to a complex nonlinear function. Right? Here, we just want to use the PDEs to replace the neural network. In the PDE model, the initial condition may be a very simple function. It's a linear function. And after some time, the initial condition evolves based on the PDE, and it becomes a very complex solution of that PDE. This is the basic idea of the PDE model. Okay. Then what kind of PDEs we can use to model this neural network? Then if we want to get a general PDE model, we have to give some assumptions. Because we want to build PDE models for the neural network, so our assumptions comes from different parts. One part is from the neural network. We want to our PDE models preserve some structure from some properties of the original neural network. On the other hand, we also want to our PDE model have some good properties from PDE point of view. From neural network point of view, we just impose these assumptions. One which is called the comparison principle. Because this comparison principle means that if the output layer, the input layer. If the output layer is has this satisfies it, if f is less than g, then after after applying the neural network, this relation also preserved. This is also very natural in the neural network because the neural network, the map of the neural network is actually the composition of these two functions. If f is less than g, after composition with the same map, same feature map, this relation also preserved, right? This is very natural for the neural network. The other assumption is a macro property. This is also very natural because the neural network is a layer-wise structure. It does not have loops. So this macro property is a natural, very natural property in the neural network, right? And the other one is a so-called linearity, linear property. This is a little bit confusing because we usually see that the neural network is a nonlinear function, nonlinear approximation in high-dimensional space. How come we say that it is linear? This linearity is it does not mean that the function of the neural given by the neural network is linear. We just see that the map given by the neural network, the function given by neural network is linear. It is also very natural. This relation, this linear relation is because the neural network is just a composition with a feature map. If this function composition with a phi is equal to this one, it's also very natural to justify in neural network. Okay, this is assumptions, 3 assumptions from the neural network perspective. And we also have some assumptions from PDE point of view. The basic idea is that this one is a so-called locality. This condition is just to make sure that the models we want to get is a PDE model. You can build another kind of models for neural network, for example, probability model or some stochastic model, what kind of any different kind of model. But here we just want to build the PDE models. The PDE model is based on the differential operators. The differential operator is a local operator. So we need to impose this assumption with so-called locality to make sure the model we get is the PDE models. These 2 assumptions are to guarantee the PDE we get is well posed or some. It has spatial regularity or temporal regularity. This is also very basic. If the PDE models you get is not well posed, it blows up in finite time. It does not make any sense, right? So we just impose some regularity conditions on the PDE models. Okay, then based on these assumptions, we can derive a general form of the PDE models. We can show that the PDE models must have this form. This is basically the convection diffusion equations. Based on these assumptions, then this form of PDE models is the only PDE models you can use. It does not mean that you cannot have other forms of the models, which only means that if you admit the assumptions we put, then this is the only models you get. You can replace our assumptions by other assumptions. Then maybe you can get other forms of the model. Okay. Based on these models, we develop a new architecture of the neural network. Then, since we have these convection diffusion equations, then we can use some numerical method to discretize this PDE, and then we can get a new architecture of the neural network. Then we develop a new architecture of the neural network, then which is very simple. This architecture is very simple. We just add a diffusion layer in the residual type neural network. It is well known that the residual neural network is corresponding to the convection equations. Since here we derive a convection diffusion equations, for the diffusion term, we just add a diffusion layer in the neural network, in the residual type neural network. Okay, after adding this diffusion layer, we can show that in the semi-supervised learning tasks, we can the performance of this neural network has some improvement over the previous one. Okay, I think I do not have enough time to show the details of the numerical examples. Okay, let's skip this part, and okay, let's make some conclusions. The take-home message is that if the labor rate in semi-supervised learning, if the labor rate is high, you can use graph Laplacian. If the labor rate is low, you can use a weighted non-local Laplacian or use a second-order model. If the labor rate is extremely low, you can use an infinite Laplacian. Or recently, we developed another PDE models to deal with extremely low labor rate. This is so-called interface Laplacian learning. We use interface Laplacian equations to model this semi-supervised learning problem. But due to a limitation of time, I do not talk about this method. And at the end, we derive general PDE models, which is just the convection diffusion equations, to model the residual type neural network. Okay, these are some references. The first reference is about the interface Laplacian learning. I skipped in this talk. If some of you are interested in this method, you can see this paper. Okay, these are some collaborators of our work, and thank you.
Thank you, Professor. Very exciting. Any questions?
Mm-hmm.
It's very interesting. Right. But another question is probably the last part of the talk is we developed this neural network based on this convex diffusing model, right?
Yeah.
You always refer the physical substance. But my question is how to introduce convexing coefficients and also this diffusing coefficients.
Oh, okay. Oh, this is diffusion equation. Yeah, this one, right?
Oh. So this is a P or this is sigma, but obviously in the previous general talk, the sigma would be in anisotropic, but here you use this.
Yeah, we just yeah, in the original in this general form, this is anisotropic. But here, to simplify this model, we just choose a constant, the isotropic and homogeneous, because that's a constant. Yeah, it's this sigma here is just a constant. It's a hyperparameter. We need to choose. Yeah. It must be choosing very carefully in your in this network. Actually, we usually we choose sigma to be 1, around 1, or then from 1 to 5, maybe in this range, And in principle, this sigma can be linear. Yeah, can be linear. Yeah.
Based on this,
Yeah, based on the data. But to learn the sigma is much more complicated. We're just trying, but we do not have some good results to for learn this parameter. Okay.
Anyway, this is very easy.
Thank you.
Thank you. Any questions? Okay, if there's no other questions, that's thank you for the presentation.